We're now going to write out a long form version of the groundwater flow equation and then make further simplifications to see what it reduces to. So we know that we're substituting in Darcy's law for the specific discharge. And so we're going to do something like this. We're looking at the spatial gradient of flow, where flow is described with Darcy's law, which involves the hydraulic conductivity and the gradient of hydraulic head. And then we're going to copy this in all three dimensions here. So the spatial gradient in the y direction of flow in the y direction. Oops. Where these are little partial derivative things. And then again in the z direction, where the subscripts here denote the hydraulic conductivity in that direction if we're allowing for an anisotropic medium, which we are here. All right. This is describing the flow into and out of the control volume. And then again, we said that over here, we're relating that to how much water is gained is gained or released from storage with this specific storage term and this idea that the head may be changing through time as water flows in and out. A few things to note. I mentioned these subscripts on the hydraulic conductivity say that it may vary in direction. So this could be an anisotropic aquifer. The other thing is that because these hydraulic conductivity terms are in the inside of this spatial gradient, we're allowing them to potentially vary in space as well. So the aquifer may be heterogeneous. If we make some assumptions, namely, if we allow this aquifer to be isotropic, so if we allow kx to be equal to ky to be equal to kz, and if we say that this aquifer is going to be homogeneous, namely, this is the same as saying, for example, that there's no spatial gradient in the hydraulic conductivity. We can significantly reduce the complexity here. So we're allowing all of these k's to be the same, and we're also going to bring them outside of the derivative because we're saying that they're uniform in space. If we do that, we get the following. We're going to get this partial term squared h partial x squared Okay, and we're still left equal with this same equation on the other side. You may be asking what happened to the negative signs. Well, there was a negative sign in our original equation when we just had the specific discharge, and then there's also a negative sign in each of Darcy's laws that we're substituting in here, and so all those negative signs tend to cancel out. So this is a more complicated, or a less complicated form. It still allows head to vary in space, and it specifically allows head to change in time, and for the flows to change in time. But there's another simplification that we can do, and that is that we can allow the system to be in steady state. So that there's no change in head in time. If that's true, then this term is equal to 0. We can get rid of this k term just by dividing it out. And we're left with this simplified equation here, where we're going to add up the second partial derivatives of each head term in all three directions. And that's all going to just be equal to 0. This is a fairly famous equation. This is known as Laplace's equation. It occurs elsewhere in the sciences. And if you have the right boundary conditions and the right initial conditions, you can solve this equation to specify the hydraulic head and flow paths everywhere in a particular system. Typically that's done with computers in a computer model, but in the next videos we're actually going to see how we can kind of ignore this complicated math and, using a fair bit of intuition and some simple rules, graphically depict how groundwater would flow in fairly simple systems.